Oh, I'm out of the camera. Yes. Yeah. Okay.
Shall we start?
Please.
Hello, everyone. Thank you for coming to our week 6 talk. Just a couple of reminders before we begin. Please try to wear your mask and social distance. If you hear the fire alarm, please leave the room immediately. And as usual, there'll be refreshments after the talk. But other than that, I'll leave Dara, who's our speaker liaison, to introduce our week 6 speaker.
Hello everyone, welcome to the week 6 talk of talks. Tonight we're very honored to have Professor Colm-cille Caulfield, who is the head of the Department of Applied Mathematics and Theoretical Physics, as our speaker. Professor Caulfield taught in many universities around the world, such as University of California, San Diego, or University of Bristol, or École Polytechnique, and right now he is here in Cambridge. I will let Professor Caulfield start his talk. Thank you for coming.
Okay, thank you very much for the invitation. I hope you can hear me at the back. My all-time favourite piece of student questionnaire comment was about audibility. Dr. Caulfield's voice is so loud, it is very difficult to sleep during his lectures. This is true, but I hope you won't, even though it's so late, I hope you won't sleep, because I find this the most fascinating and interesting, and I hope by the end of the talk I will convince you the most important problem facing physicists at the moment. I'm really interested in how stratified turbulence, the turbulence in a stratified fluid, mixes up the world's oceans, which is a key controller for the climate. And really what I want to demonstrate today is that at a combination of large-scale numerical simulations like this, of a breaking internal wave, and I'll talk a bit about what an internal wave is, as well as reanalysis of observational data using the tools of the sort of trendy area of artificial intelligence and machine learning, can really get us somewhere to improving the way that we model the world's climate. And of course, I have to say thank you to my sponsors. So this is an amazing video put together by Kathleen Doan, a friend of mine who works in Washington State in the US. And this is ocean surface currents from altimetry in real time. So satellite measurements of the height of the sea surface can, when you apply them to fluid dynamical equations, can show for you the currents that exist in the world's oceans. And the most important thing I want you to draw from this is that the ocean, there are many currents in the ocean and they're doing lots of interesting things. Right? So here is, I mean, it's a bit dark, but here's the British Isles. That's the Gulf Stream up the west coast of, the east coast, of the west coast of the ocean basin, the east coast of the United States. There's a similar western boundary current here. It's called Kuroshio off the Japan. And here, this is the Agulhas current, and you see that it comes down and then is turned round by the amazing flow in the Southern Ocean. There is a vast flow spinning around, it's the sort of global flywheel around Antarctica, transporting water of the order of 100 million cubic meters per second. A lot of water. You'll also see, and this is a beautiful demonstration of the fact that this is not an inertial frame of reference, you might wonder why you see these strong currents at the equator. And that is, of course, because the component of the Earth's rotation is changing sign, and you actually can see it in the world's oceans. So that's pretty cool. But, of course, what's not cool is the world's oceans. We're really heating them up really rapidly because we're heating up the atmosphere. This is from 2 years ago because I get too depressed about cutting pictures out of The Guardian. But you see this steady trend of the fact that the world's oceans are heating up. And why do we care about the fact that the world's oceans are heating up? Well, the world's oceans are the key controllers of the global climate system. Don't let any atmospheric physicist tell you otherwise, because there is so much heat in the world's oceans. The heat capacity of the world's oceans is quite astounding. It's kind of been in the news because it's all about billionaires in phallic rockets, that the edge of space goes out to about 100 kilometers. That's called the Kármán line. That's the Bezos edge of space, because that is the place where a plane can no longer flies, it orbits. That's really a very good definition of the edge of space, one would argue. But you can imagine that defines a column of gas in the world's atmosphere, right? Think of a cross-sectional area at the bottom. You then have a given volume of gas. And you think about, okay, as we add carbon dioxide, we're going to heat that air up by a degree, let's say, whatever, degrees you like, Kelvin, centigrade, Fahrenheit, doesn't matter. A certain amount of heat has got to go into that column of gas to heat it up by 1 degree. The same amount of heat is required to heat up an equivalent column that is only 3.4 meters deep in the ocean. The amount of heat capacity of the ocean is incomparably larger than the heat capacity in the atmosphere. And so it is critical to understand how heat is transported into and out and around the world's ocean to understand how it affects the global climate system. Here's also the poleward transport of heat in the world's oceans. The total is about 2 petawatts. That's 2 to the 10 to the 15, and a kind of abuse of units is that is 2 billion kilowatts, right? So that is as if everybody in Europe was continually having a blow drying their hair, pointing the heat northwards, right? The heat that is being transported in the world's oceans is enormous and is really dominating, is causing these sorts of currents that we see going round. And a key thing to understand about those currents is while there is still some ice on Greenland, we get cold water, deep water forms and sinks near Greenland. It sinks in the Southern Ocean and then goes to deep depth. And then there has to be something within the world's ocean that mixes it up, because otherwise we just have a hot layer near the top, which is just purely being heated by the incoming solar radiation, and the cold water from the polar regions at the bottom. There's got to be some mixing mechanism that stirs the ocean up so that we have a vertical stratification in the ocean. And understanding how that stirring up happens is critical for the billion and a half people who live near coasts. Because as we're heating up the ocean, there's 2 things that are happening. The ocean is expanding, because as you heat up, water's weird, but as provided you're far enough away from 4 degrees, as you heat up the ocean, it gets less dense, its volume increases. So you heat up the ocean, that causes 30–40% of global sea level rise, and the rest is land. We all remember Archimedes. It's land-based ice being melted from Greenland and that is on Antarctica. As that is melted, then we are going to increase sea level rise. And there is a huge amount of uncertainty, but this is measured in millimeters, so in centimeters, that the sea level will rise 50 meters, 50 centimeters. Doesn't sound like a lot, but 50 centimeters will very, very much affect. It's the end of the Netherlands kind of thing, right? If you have a 50 centimeter rise in the ocean. So why do we have so much uncertainty in the future predictions? Well, there's 3 areas of uncertainty. Clouds, principal uncertainty. Clouds, it's really, really hard to model clouds. The droplets form on the scale of microns, and they can be 100 kilometers across. It's really hard to understand ice sheets, because as they melt, do they break up? Does it go off the land? Does it melt? How does the phase change occur? Both of these are complicated multi-phase flows that I don't want to talk about. But there's also this other one, the internal waves. Internal waves that are waves inside the ocean that are analogues of the surface waves you see at the top. But you have these waves inside the ocean. Why? Because the ocean is stratified. I said there is density variations. And as soon as you have density variations in a fluid, you have a restoring force, which gives you the chance for simple harmonic motion. Okay, so here is the idea. Let's start with this one. So you have a density gradient, so more dense fluid near the bottom, less dense fluid higher up. You conveniently color-coded light blue. And what is more dense than light blue? Dark blue, Oxford, understand that. Light blue is on top. So you lift dark blue up, it gets above its station. It feels a restoring force that means it wants to return to its equilibrium position. But a classic simple harmonic motion issue, when it gets back to its original location, it has some velocity. It's changing potential energy into kinetic energy. It overshoots, and so it oscillates. It oscillates at a characteristic frequency, this frequency called the buoyancy frequency, which is you've got to have a gravitational force and then is linearly related to the density gradient. But fascinatingly, if you then force at a frequency, if you oscillate something at a frequency lower than this characteristic frequency, which is what I'm going to show in this video here, what you have is a bar that's holding a horizontal cylinder. And the bar, and it's stratified fluid. And when the bar moves, you pull the cylinder backwards and forwards in the fluid, and you set up waves. You set up these waves which have a really cool property. You see the phase fronts goes down, even though clearly the energy is going up in this section, and the phase fronts go up, even though the energy is going in this direction. These are called internal waves. And because the ocean is stratified, these waves are everywhere in the ocean. The ocean is basically a soup of loads and loads of different waves of different length scales and different characteristics. They're all over the place because if you imagine a current that goes over topography, you lift a dense parcel up and then it falls back down again, you get waves. But you not only have currents going by, you have tides in the ocean, the waves will go backwards and forwards. If the waves encounter topography, they will be scattered. And if they interact, and if you have storms at the surface, the storms at the surface perturb the upper mix layer, which is mixed by wind and turbulence, and it perturbs the boundary, the thermocline, downwards or upwards, and that will trigger waves too. So you've got to think of the fact that the ocean is full of waves, and if the waves break, that is how you're going to mix, you're going to lift dense parcels up, you're going to have the heat transport, you're going to have the stratification changes. So really, in terms of the remaining part of the talk, I'm going to be looking at two particular parts of this problem and see what I can talk about. I'm going to look at observations of waves that are caused near boundaries, near reefs, and say, can we understand the mixing properties associated with that using machine learning techniques? And then I'm also going to look at a very, very idealized cases, you know, like that you should think of like a cube out of the ocean and in a simulation and say, can we understand how this sort of wave breaking process, what sort of mixing events could happen? And that's really associated, motivated by this amazing man, Walter Munk, and this amazing paper he wrote in 1966. Because he identified, I'm sure you can't read it, but it says vertical distributions in the interior Pacific, excluding the top and bottom kilometre, are not inconsistent with a simple model involving a constant upward vertical velocity of about 1 centimetre a day and an eddy diffusivity of about 1 square centimetre per second. Now, an eddy diffusivity, I'm sure at least some of you have encountered diffusion equations. You know, you have a hot bar and a cold bar and then heat, and you muck around with Fourier series and you get perfect marks on your exam question and you're all happy, right? But the key rate at which this happens is the diffusivity. It's the rate at which the diffusion happens. Now, turbulence can be thought of as a way that it diffuses momentum because it enhances the rate at which you smear out velocity differences. And it also helps to smear out density differences, so it speeds up the diffusivity of heat. And that mathematically corresponds to this fudge here, that you really, if on average you lift dense parcels up in the flow, so vertical velocity W and density fluctuations are positive, that is like a diffusion in this sort of picture that we want to have, because the idea is we want to stop the cold water from Greenland, we want to lift some of that cold water up in the interior. And we want to relate that through this eddy diffusivity to something that's much easier to measure, the density gradient, which I've already introduced, this buoyancy frequency. So the whole devil is, how can we model this? Because Walter Monk's back of the envelope said that it should be 1,000 times, the effect of turbulence is 1,000 times bigger than diffusion just due to thermal diffusion like you do on your example sheet. I'm sure I'm going to run out of time, but I have to tell you, this guy died when he was 101, and 5 years ago when he was 97, he gave a talk in a session at a conference, the Ocean Sciences Conference that I organised, and it was original stuff. Terrifying. Of course, terrifying that he didn't retire, but also amazing how bright he remained. Amazing man. And the other story of him, he was the guy who modelled how stormy it was going to be on D-Day. And he convinced Eisenhower to wait a day because he understood ocean waves best. The original day for D-Day was not the D-Day, but it was the day before. But he told Eisenhower to wait because it was so stormy. And he was right. Amazing man. Anyway, that's back to the maths. So that's the key question. How do we get this complicated second-order correlation in terms of mean gradients? Well, we write down an equation for the kinetic energy, which is the Navier-Stokes equation dotted with velocity. So we have the rate of change of the kinetic energy. We have some divergence of a quantity. Remember our divergence theorem? You know, this is just a flux through a surface, right? So that will just, and so if we're in a controlled system, this is just moving energy around. It's not creating or destroying it. Viscous dissipation is destroying energy, but kinetic energy is being converted into potential energy if we've got to lift dense parcels up. And we might indeed also have a forcing term and also turbulent production, because if you have a velocity shear in the system, if I lift a parcel up in a velocity shear, I can give it momentum by pushing it along. So this is the terms that I have. And this is the fundamental picture I'm trying to understand. If I have turbulence in a stratified environment, how much of that turbulence is turned into lifting dense parcels up on average, which is this sort of well-mixed picture? Could do nothing, could do something intermediate, or it could do the solid blue line and form a perfectly mixed volume. Now, if it forms the perfectly mixed volume, I've on average lifted dense parcels up, so I've turned kinetic energy into potential energy, I've taxed the turbulence. So that really reduces to asking the question, if I have a certain amount of energy being put in by the turbulence through the turbulence production, how much on average goes into lifting dense parcels up and how much goes into viscous dissipation? But the problem with this formulation is that I could just, if I lift a dense parcel up, I could just as easily put a dense parcel down. This has a reversible component. So it's difficult to separate the irreversible component associated with mixing with the reversible component associated with stirring. So a beautiful idea, really due to Osborne and Cox is the thing, is to say, well, you know, the kinetic energy can be thought of as the square of velocity fluctuations. Why don't I look at an equivalent quantity, the square of density fluctuations? And if I write down an equation for the square of density fluctuations, appropriately scaled so it looks like an energy, and if the background gradient were just constant, this is exactly the same as a potential energy, which is a freaky bit of maths that you'll have to believe me. You have a transport term, but then you have the buoyancy flux term again, because of course the way the potential energy will increase is by pumping in potential energy. But you now have this quantity chi, which has the diffusivity in it, but is very like, because this involves velocity gradients and now this involves density gradients, this is the destruction of buoyancy variance, or in a certain case is the destruction of available potential energy. Just like viscous dissipation is the destruction of kinetic energy, the chi quantity is the destruction of available potential energy, or more precisely the destruction of buoyancy variance. So if everything is kind of behaving simply, then the question of what the taxation rate is B, well then you expect this B to be the same as chi, and chi has the nice mathematical property that it's definitely positive. It's positive definite because everything's squared, nice and reliable. We haven't got any complex numbers here, so every squared, I'm definitely sure it's real. So, and positive. So, the traditional thing is this taxation rate. Can we understand a quantity called gamma, which is basically the ratio of chi to epsilon, which is how much of the energy that's been lost from the kinetic energy that's been lost from the flow that goes into viscous dissipation, i.e. increasing the internal energy, and how much goes into changing the potential energy, i.e. lifting dense parcels up. And this is important because it's what's observed. These are observations from 20 years ago. You certainly can't read the signals, but what they identify is that they seem to see viscous dissipation right exactly where you would expect to see these sorts of wave-breaking turbulent events, which is when the shear is strong compared to the density gradient. And that's kind of energetically what you'd expect. If there's a lot of kinetic energy in a background shear, like this breaking wave or like this overturning Kelvin-Helmholtz billow, then you think you've got enough energy to lift dense parcels up. So you would hope that there is a good correlation, which is exactly what's observed here, between mixing events and where this particular ratio, called the Richardson number, is small. And why is it? Because if it's small, it means it's very easy to lift dense parcels up, and you have a lot of energy in the kinetic energy field. So that sounds reasonable. But then the question is, well, why should that be the most important parameter that we might want to have for the mixing event? Because there's a whole load of different parameters that things could depend on, right? And they can be classified into at least 4 different categories. You could have the properties of the fluid, how viscous the water is, and how rapidly the heat diffuses. And I'm not even getting into the fact, which maybe has occurred to several of you, that you also can have salt cause the density variations in the ocean. And so then salt diffuses much more slowly than heat. And so you can have phenomena called double diffusive effects. It's about one diffuses more rapidly than the other. You get very strange layered dynamics. I haven't got it. Of course, you have a nonlinear equation of state. We all know that water has its maximum density at 4 degrees. But that is actually pure water at atmospheric pressure. I've got a room full of physicists. They're not going to be freaked out with what I'm about to tell you. There is actually a situation the way water changes, right? So that you can, if water has salt, heat, and pressure, God love thermodynamics, you can have a situation where a parcel of fluid at this pressure, the parcel on top is less dense than the parcel below, but if a wave goes by and causes it to go downwards, it is entirely possible, it's called cabling, and the thermobaric instability, that now the parcel that's on top, its salinity hasn't changed, its temperature hasn't changed, but because the pressure has changed, the equation of state means that this parcel is now more dense than the parcel underneath, and you get convection. That happens in the world's oceans. Really freaky. Why anybody does quantum mechanics or cosmology is beyond me, because there's so much beautiful things going on in the world's oceans. But you have really weird physics going on with the nonlinear equation of state. But I'm not going to talk about that anymore. There's the properties of the background. You might measure what the density gradient is. You might measure what the velocity gradient is. You might worry what you mean by averaging. But those are properties of the background. But then there's the properties of the turbulence, right? How intense the turbulence is, how intense the viscous dissipation is. You'll see the dissipation is related to contraction of the gradient tensor of the velocity field. And also, equivalently, the properties of the density fluctuation field. So you have a whole load of different parameters that you could have. So how these affect things, who knows? Now, the classical model is really an Occam's razor model, is to say, well, all these different things are going on, but the most obvious thing to say is there is a constant taxation rate. In other words, the buoyancy, this density flux, vertical density flux, is directly proportional to the viscous dissipation, and so then about 20% of the energy, well, about 20% of the, if the density flux is 1 unit, then the dissipation rate is 5 units. It's like making a martini, right? So just like the components, right? But that's the standard argument. But actually, there's a whole load of, but in truth, you'd expect gamma could depend on a whole load of different parameters. The Prandtl number, the ratio of the diffusivities, this Richardson number from the background properties, a turbulent Froude number, which is how strong the turbulence is compared to the background stratification, and then even a combination of which is called the buoyancy Reynolds number, which is really the ratio of the time scale of the viscous dissipation of the turbulence compared to the time scale of the stratification. Could depend on any one of those parameters, and we really don't know, right? And so there's been a great amount of debate in the literature. These are, you'd expect a review article to kind of tell you something certain, but a review article, Greg Ivy's actually from Australia, but this is very much comes out of Stanford. And they basically say, laboratory and DNS, direct numerical simulation, indicate that when the buoyancy Reynolds number is 1 or when it's 10 to the 5, the mixing efficiency is 0. And the use of this standard value in field observations cannot be justified. That's what was said in 2008, right? And then 10 years later, a group of scientists in Washington then said, it's long been understood that mixing efficiency is unlikely to be constant, but saying the diffusivity evaluated saying the mixing efficiency is 0.2 actually agrees better than simulations and experiments. So we don't know why it works, but it works. And this is a fundamental problem. So we don't know, they didn't know. And then I was lucky enough to I was asked to write a review article. And then I said, although there's been a large range of deeply insightful research contributions that's been polite to other people, it still remains extremely difficult to say anything generic about mixing. We have no idea what's going on. That's not exactly what I said in the published paper, but I'm a bit nervous about review. But it's basically, we have no idea, right? And so I kind of said, I wrote down that is it worth investigating whether data-driven techniques such as machine learning and AI can be applied productively to model stratified mixing. And that's really, this talk is really in two parts, right? The first part is about, it's an important problem, and it's really challenging, and it's very complicated. And then I'm going to just revisit two things, an observational data set and a numerical data set from enormous numerical simulations with 270 billion grid points per time step, gigantic things, to try and see if we can use automatic data-driven techniques to extract useful information. So let's talk about the observational data. So this is the island of Palau. That's Australia. So it's a really rather pleasant bit of the South Pacific. Conveniently also, Hawaii is a very interesting place to study, to do field observations. The North Sea, not so much. So these amazing measurements were taken just off the coast of Velasco Reef, off this Palau. And they were vertical measurements with this amazing profiler, which can take vertical measurements on centimeter scales of the dissipation rate epsilon and the chi. And you can see this amazing amount of structure in the data. And so we thought, well, can we do machine learning to try and identify different mixing events? So what we did, we being defined here as a brilliant postdoc of mine, Miles Couchman, did a window and windowed the data, constructing patches of data in windows, taking snapshots as you go down, of the epsilon, the dissipation rate, of chi, and also they measured the density gradient, so of the n squared quantity. And then he creates this big matrix of data that has these various properties. And then the question is, how can we identify useful information from that data set? And what we really want to do is we want to identify things that are the same. You know, it's not entirely unrelated to the classical problem of can you identify pictures of cats and can you identify pictures of dogs, right? But what we want to do is we want to identify mixing events that have the same kind of properties from within all these lines of data. And how we do this is using this particular algorithm called optics. And what it wants to do is it wants to identify, it's two fundamental characteristics we're interested in. Finding a group which is tightly bunched in terms of its properties and is in a tightly bunched group of properties. We don't want, we want to identify something that we can then talk about generically. And so what we do, remember I said it's epsilon, the dissipation rate of turbulent kinetic energy, chi, the dissipation rate of buoyancy variance, and n squared, the background density gradient. And that, if you think that triplet defines a point in three-dimensional space, right? So you just plot it in 3D space. And then you say, okay, how far is it? How big a sphere would I have to draw around that point in three-dimensional space of that particular data point to contain 999 other data points? Right? If that sphere is small, that means the data is very clustered. If a sphere is big, it's not clustered at all. Right? And then I consider a pairwise measure. I do this for one point and I do it for another point. So I work out how big the sphere is around xi to have 1,000 points in it, how big the sphere is around xj to have 1,000 points in it, and how far apart are points xi and xj. So that measures whether they both are in a big clump, a dense clump, and also if they themselves are close to each other. So if I take the maximum of those three measures, the core distance, i.e. the size of the sphere for xi, the size of the sphere for xj, and the Euclidean distance apart of the two of them, i.e. how far apart they are. That then defines a reachability distance. That shows you how easy it is to go from point xi to xj in a busy clump. And then I get all my data sets, and I line them up, and I see if I have points that have very small reachability distance relative to them. Because you see, for example, the red clump, they're very close together, and there's a lot of them. So there's a whole lot of them that it's very short distance, this reachability distance. But the yellow points are really quite scattered, and so their reachability distance is really quite far apart. Right? So we do this to the data, and we're able to find if we can find clumps. And we change the windowing distance, and we change the number of endpoints, and we write supplementary materials, and faff, right? I'm going to show you the data. And this is amazing, right? These are 2D projections of that 3D space. Remember, I'm sort of saying we've got epsilon. Epsilon is the x-coordinate, chi is the y-coordinate, and the z-coordinate is n squared. So this is a projection of epsilon and chi. This is a projection of epsilon and n squared. And this is a projection of chi and n squared. And we found 5 clumps, which we colour blue and purple, because those clumps are associated with regions of weak stratification. You'll see they're low down here. One of them has it's centered on a low value of n squared and a low value of dissipation, and the blue is at a higher value of dissipation, but still low n squared. And then these high n squared, you see there's clear blue water, so to speak, between them and the yellow, the orange, and the red, which are at higher n squared, but are ordered by the value of epsilon. And also, you can see ordered by their value of chi. Right? So we found 5 clumps. And now what we say, okay, we did it on epsilon, chi, and n squared. Now let's look at other measures we have. For example, I haven't told you that we also knew where they were measured in terms of how far offshore and how deep. So we had 2 coordinates in that sense. We knew when they were measured, because I'm going to tell you there's the extra bit, they were measured in 2 separate days, and which tells you there are different currents. And we also measured the velocity shear. Remember that was from the Richardson number? And here's the plot of those centers of these different data, the mean value. This is epsilon. It's the logarithm of epsilon. So these are quite big differences. This is chi, the mixing of the density. And this is the shear. And you see that the hot colors lie on a perfect correlated line, right? They are, so as I increase the shear, I'm increasing epsilon, and I'm increasing the mixing. But the low n squared are not like that at all. They have quite different values of shear. They have no mixing at all. And there is a correlation between shear and, because the higher up it goes, the further to the right it goes. The correlation between shear and dissipation, but not with the mixing. So now let's think about where these different mixing events are located. And this is amazing. Well, I think all this is amazing. It's great. So this is the distance off the coast in kilometers. And this is the ocean floor. And so you see, though we didn't sort the data on their location, they really, really are sorted on location. The blue stuff is, the blue mixing event is at high levels and is near the shore. And the purple stuff is at low levels and far offshore. This is the typical mean density profile. And so both the blue and the purple are centered in places where the stratification is really quite weak. The blue in the upper mix layer, which perfectly explains, therefore, why the dissipation rate of that guy is larger, but the purple at low levels offshore, where there's not much stratification, but there's not much turbulence either. And you'll see the hotter colors, the reds, the yellow, and the orange, are all in the region of high density gradient in the thermocline, which itself is a bit surprising. But the colder the color gets, the further offshore it goes, which shows that with this method has managed to identify for us the near-shore mixed layer mixing events, the deep mixing events, and the in the thermocline, near shore, far away from shore mixing events. And they've also managed to identify for us the different days. So you see the blue data set is dominated by day 2 when the current was in this direction. That's what that shows. And the purple data set was dominated by day 1 when the current was in that direction. And you see, but it was in that direction near the surface, but there was a return flow down low which caused shear, which caused these kind of instabilities, which is associated with why we have a lot of purple. So we are able to identify when the mixing events occurred, that we are able to we sort on the epsilon, chi, and n squared, but we're able to therefore identify characteristic mixing events from different days and different locations automatically without doing any artificial averaging. And what then leaps out, even more curiously, remember I told you that the key assumption of Osborne is that chi is pretty much the mixing is linearly related to the viscous dissipation. So that would mean that chi should be linearly proportional to epsilon. And so Miles had this brilliant idea of saying, right, since we're plotting the logarithm of the dissipation rate and such like, we have very large differences. So the shaded regions are the regions that contribute 80% to the total of what's going on. And there's quite a bit of shading in the epsilon. But there's very, very little shading in the chi. Chi is dominated by extreme events. And another way to understand that is here. If we order the points where the ones at the left are the ones that have the most mixing associated with them, and then we add them all this is the 30th percentile so that is the highest amount of mixing in terms of ordered points we've measured. And then we look at their contribution to the total, something leaps out. Epsilon, it doesn't matter which mixing event we're interested in, it pretty much follows the same trend. You see the curve is identical. But the chi, the dashed lines, are separated depending on the color coding. And rare events do most of the mixing. Because, for example, for the red one, 80% of the mixing is done by about 7% of the points. So rare events do virtually all the mixing. For you to get to 80% in the dissipation rate, you have to look at 25% of the points. So chi and epsilon are not linearly related, and extreme mixing occurs even when extreme turbulence is not occurring, which is really quite curious. And what that means, once again, if we look at this weird gamma parameter, the ratio, the taxation rate, we have this very strange relationship. Remember, the canonical rule was 0.2. So for an awful lot of the data, you get 0.2. So if you do a few measurements, that is what you're going to see. You're going to see 0.2. But there's a tail which kicks up a lot. Now, the dots are the mean when it's ordered by how much mixing they do. And the shaded region, which once again doesn't display very well, is the 25 to 75th percentile of events. So it's only rare, so it's a very, very skewed distribution. Rare events happen much more frequently, make a much bigger contribution to the thing than the typical values. And so if you do measurements, you may see the mixing events that have gamma is 0.2. But you are missing the ones that are doing virtually all the mixing because they have much higher values of gamma. This is the log 10 of gamma against the amount of mixing. And those are the percentiles. And you see a lot of the events are centered around 0.2. But then there's a fat tail where they kick up to much larger values, to the log 10 of 1. It's really 0 is that it's gone. Remember, this is 0.2. This is the 0.2 value, so that's saying it's 1 to 5. 0 is saying it's 1 to 1, and there's still a lot more going on. So we're also kind of curious about those kind of events. We call them Goldilocks mixing events, because they are just right to be very, very efficient at the mixing. So, but by doing this sorting, we've managed to identify that there are different kind of mixing events in the ocean, and there are rare events do a lot of the mixing. But then the question is, okay, well, poor old oceanographers have to go out and take profiles. How many profiles do they have to do to be sure they have a good representation of what they're measuring? And the way to do that, to investigate that question, is to then consider numerical simulations. And I'll tell you why. Because numerical simulations means you're able to look at a block of fluid and imagine that fluid. You can then take profiles through it as if you're an oceanographer, but you're God. You know everything that's going on in that cube of fluid. So you know what the real value you're trying to do, but then you can see how many measurements you have to take to get a good statistical estimate. So that's what we did here with my colleague John Taylor and Paul Linden, my former PhD supervisor, and a guy called Steve de Bruynclops as well. What we did was we did a numerical simulation of a cuboid of fluid, and then we used these different theories. I mentioned Osborne and Cox. You can also do it on the scale of the overturning, which is named the Thorpe scale method. He was my PhD examiner. And then you can do the direct measurement, actually use the buoyancy flux, and as I told you, the buoyancy flux gives you the wrong estimate. So these are for 3 different simulations. The dashed line is the real value of the kappa, the real mixing that's going on in the box, because we're able to measure it because we're God. And the bands show you the statistical estimates you get from taking 1 profile, 5 profile, 10 profiles, and so on, using these different theoretical approaches. The Osborne model, the Osborne-Cox, which is not involving epsilon at all, just looking at chi, the scale of the overturning method, the Thorpe method, and using the buoyancy flux. And you'll see that the blue method is the Osborne-Cox method is probably the best, but doing it randomly, you can still have really quite large error bars, even when you're taking 20 profiles through the same box. And so the question that we wanted to ask is, well, can we do better than just taking random samples? Can we try and use a neural network to, from a much smaller set of samples, develop a better model for actually what we expect the turbulence to be than these theoretical estimates which are based on, looking at the equations? And that is really a statistical statement. It is, can we take a measure in a numerical simulation, do one of these drops, and then ask the question, what is the most likely statistical distribution with a given mean and variance of the real mixing that is consistent with these observations that we've taken? So we're not actually necessarily interested in getting ideas on averages. It's much more information about uncertainty. What is the maximum likelihood of the mean value and the variance of the real distribution taken from these set of samples that we've measured? And that's what we did. Because there's another dirty secret that's going on in these observations. I told you the real thing that you're interested in is the dissipation rate, which is this contraction using Einstein notation of the gradient tensor. But you actually suppose that it's simple, that it's the modeling, it's much easier to measure horizontal velocities and how they vary vertically than all the other components. And so what you really do is you just measure the velocity in one direction and how it varies with depth, the horizontal velocity in this direction and how it varies with depth, and just say that the turbulence is homogeneous and isotropic, so it doesn't matter about the direction. But here's a simulation of stratified turbulence, and that is, in the words of Douglas Adams, almost but not quite, totally unlike, entirely unlike homogeneous and isotropic, right? It knows which way's up, it's got this very layered structure, we don't know what. So the idea was, let's look at very large numerical simulations with hundreds of billions of grid points and treat them as measures, blocks or bathtubs of the world's ocean, and drop profiles through them at different time steps and run a neural network on it. So what we do is we take these boxes of what the turbulence looks like. This is a plot of the dissipation. We drop profiles through it of a short, relatively short distance. These are, like I said before, it's 8,000 squared by 4,000 data points. So we do it through a restricted part of it, just 500 grid points. And then we look at what the shear is and what the density gradient is, which is what we would normally have for the classic models. And then say, okay, well, this is the observational data, the data for this training data set. And so we get a correlation between what the actual dissipation rate is and what the measured things is. And so then we get better estimates. We assume the turbulence is distributed with a Gaussian distribution. And we say, well, what's the best estimate for what the mean value is and variance? And then we do this over and over again using a convolution neural network. So, you sort of march through the different pixels like this video is here. And you keep changing your parameters in your convolution layers until you get the best estimate of what the probability density function should be for the epsilon that is associated with those training measures that you've done. Okay? You do that on a training set, and then you say, okay, let's look at other data sets. And this is this bit of magic that's here, right? So the DNA, so we go somewhere else in our computational data set, and what we measure is the shear and the density gradient. And then we say we have this model of what that then tells us what the Gaussian, what the mean and the variance is for this assumed distribution of epsilon, and then sample from that data set several times to construct profiles, and then compare them with the real profiles when stacked up together. And here, this is a vertical line, and it's turned on its side. The numerical simulation is the black line. This probabilistic neural networks prediction is the red line, and the shaded red region is the variance. And it is the uncertainty around that. And that so qualitatively looks like this, right? It really does seem to have captured the nature, this anisotropic nature of the turbulence. And so if we compare at the different time snapshots we have in this decaying turbulent event, if we compare our probabilistic neural network, which is in light blue, and the DNS, which is in black, in this room, you can't see the difference. There is a little difference here at the later times, but really the two lines are right on top of each other. But supposing the flow is this surrogate model of it being stationary, homogeneous, and isotropic turbulence, don't think of the acronym, you have a really enormously wrong answer. At the early times, the means are kind of okay, but they then start to drift apart. But the entire structure of the distribution is completely wrong. And as I was talking about before, what really mattered is the tails of the distribution, because that's what we really need to know about the extreme event. And the tails of the distribution between the black and the light blue is very good, whereas the tails of the distribution with the surrogate is terrible. Right, so that is finally the conclusions. I've tried to convince you that turbulent stratified mixing is very important. I've tried to convince you it's very hard to understand. I've tried to convince you that extreme events matter. But I've tried to show you that if you use machine learning, you can identify interesting properties, but you also should be thinking about the calculation statistically. Because what you want to know is not, because you are always going to have a restricted set of data that you want to generalize from. So what you really want to know is the properties of the distribution from which you are sampling more than the particular values that you've actually done, which is a change of mindset, really, about how you do things. So future work is we're going to even bigger and bigger calculations. We've just finished a simulation on the fastest computer in America at this resolution. It's just madness, right? You have billions and billions of data we need to analyze. We have hundreds of time steps with trillions of data of the three components of velocity and the density, and we're trying to extract information from them. So thankfully, I have very bright people who do all the hard work. Miles Couchman, who's a postdoc working with me, he did the problem with the Palau data set, which was measured by this group from Scripps Institution of Oceanography in San Diego, Matthew Alford, Jen McKinnon, Gunnar Vogt, and Bethan Wynn Katanak. And the probabilistic neural network, that work was led by my PhD student, Sam Lewin, and Steve de Bruijn-Kops, who's at the University of Massachusetts, and Gavin Portwood, who's at Lawrence Berkeley National Lab in the US. Steve does the simulations, Gavin's the sort of more machine learning guy, and Sam's the brilliant kid who brings it all together. So, thank you very much for your attention.
So thank you for the talk. So you said, yeah, like extreme events like really matters, and like that fact like really like reminds me of like power law distribution, and like when you have like power law distribution, there are some like feedback groups, and so you think there are like some feedback like mechanism in the ocean?
Yes. Yes. So that's an extremely on-the-spot question. So subliminally, I flashed. Yes, it's written at the bottom, and it's something I'm very much involved in debate with people in the literature, because there is something that's very suggestive that the ocean is tending towards a marginally stable state. Now, the power law that you kind of mentioned, it also comes from, the physicists encounter this, the self-organized criticality phenomenon, right? And so there is some hints that we do indeed have these sort of power law distributions. So self-organized criticality, it's why a sand pile looks like a sand pile, right? So you have a sand and you slowly drop sand onto it. It tends towards being in the angle of repose, i.e. the sand particles, there's just the balance between gravity and friction that means they won't roll, right? And you add a little bit more, you have a little avalanche, and so the pyramid, the sand pile organizes into a perfect conical pyramid. It self-organizes into a critical state. That has two characteristics. It has this marginal stability argument, and it also has this power law distribution this chap's talking about how things behave. There is not very clear evidence that we have power law distributions. Indeed, we don't really think it is anymore. We think it is a skew log normal distribution. So the dissipation rate, what you're observing in the ocean is a sum of mixing events, because the waves don't all break at exactly the same time, at different stages in their evolution. Each one of them, quote unquote, individually log normal, but when you add them all up, you get a skew log normal distribution, which kind of looks like a power law. So there is a hint, however, that the flow is marginally stable, that the Richardson number in the flows organizes to be right at this sort of critical value of around a quarter. There's a lot of evidence of that. More places we look, the more we see it. And there's also, which is this kind of idea we talk about, Goldilocks, that the two particular length scales in the flow, another thing goes into critical relationship. The length scale of the characteristic overturning that you see, the video is perhaps not running. Yeah, my movie, yeah. So the length scales of the overturnings that you see become exactly matched with the length scale that you construct from the properties of the turbulence and the stratification, which is effectively the length scale that you'd expect a turbulent eddy to just have enough kinetic energy to turn into potential energy in one overturn. It's called the Osmodov Scale, after a Russian guy called Osmodov. And that is a scale that relates the turbulence to the background stratification. When that scale is exactly the same, or very close to, the geometric scale, which is associated with actually seeing an overturning parcel, then the fluid, A, that seems to be very common, and B, it seems to be extremely good at mixing, which allows you to remain in this marginally stable state. So that was a very long answer. It was as if you have read two of my more recent papers, because that's what we're really banging on about. Yes?
I have a question about the sampling that you talked about earlier. There is, when you talk about the number of samples that's required to achieve good accuracy with respect to the actual things that we measure, then does each of those that we take, does that influence where we take the next?
No, no, I wasn't clear about that. No, this was, you imagine it's the computational size of these boxes that we're able to get. They're of the order of 10 meters or so to have the flow properly resolved, 10 meter cubed volumes. It's like a swimming pool is what we're really sort of able to simulate, which is so pathetic compared to experimentalists. And they were randomly, we dropped the samples randomly in that space. It was deliberately done, completely uncorrelated. We just had a random, there was, you know, there's a surface cross it, you know, there's kind of 8,000 by 8,000 on the top surface, and you just randomly select one of those numbers and drop a profile through it. And that's how we did the 50. So they were completely deliberately uncorrelated.
Why don't you use data from one particular profile and use that to motivate where you drop the second profile?
Oh, because the idea, what we were wanted to know was that how many randomly, we wouldn't know where we were in a particular mixing event, or you know, wouldn't have any physical insight, you know, the ocean's opaque. So we drop a profile, and then we want to have some idea of how much confidence we should have in the value we extract from that individual profile as an estimate of what's really going on average in the box, right? And so it's like, you know, how many darts do you need to shoot in to be confident to kill Schrodinger's cat, right? You know, and it's that sort of thing. We didn't know, and I mean, it sounds simple, but I think that this is a very simple idea of a paper. But I think the point is, it was a little disappointing to the observational oceanographers, or it's made them really stop and think, because, you know, if you take 20 profiles, you could be estimating anything, you know, look at using the direct method on simulation B. I know it's the worst one. You could have a value between 0 and 4 would be what you would be saying, and the real value is 2. And after doing 20 measurements, that's the sort of level of scatter that you have. I mean, it's really worrying. I mean, you know, global climate change is definitely happening. It is really, really, really concerning. The problem, the real challenge is to be able to predict accurately how bad it's going to be. You know, like this, was at the heart of the discussions in COP, right? You know, it is 1.5 the point of no return, or is 2, right? That gets right to the heart. And they are based on models, because they're predictions of what will happen. And there is actually uncertainty in those. It's a real, I mean, it's a bit worrying with being streamed. It is absolutely real, but there is uncertainty. And we really need to narrow that down, and that uncertainty, because because any number of different reasons to inform policymakers, not that the policymakers of this country would listen, but the point is, there's even the utilitarian point, which is what is more important to address, right? You know, is it more important to address deforestation? Is it more important to address changing agricultural land use? Is it more important to address carbon dioxide to ensure that the ocean stops mixing, right? There are real order one uncertainties. You know, so for example, being unsure in 2 degrees of the heat of the temperature of the Southern Ocean will profoundly change what happens, right? What the consequence happens. It doesn't sound like much, but it's enormously important, because when you're mucking around 4 degrees, there's a huge difference between 2-degree water and 4-degree water. Literally in the direction in which it will go. Will it keep going down, or will it stay up? And it's just really, so that's the motivating point of trying to do this, is to try to, what is the best way to reduce uncertainty in models? Yeah.
Are there any physical conditions that make this kind of extreme mixing events more likely? Or is it just
There are. Now let me be clear. Do you mean the extreme events that I'm talking about, that I was talking about here, or do you mean like the extreme events of, you know, hurricanes and so on?
No, I mean like extreme mixing events.
Yeah. So yes, I'm glad you asked that. That's what this particular picture is trying to be a kind of representation of, is this phenomenon that I refer to as these Goldilocks events. If you manage to have so if you have a shear layer, i.e. you have vertical variation in velocity, that is actually can be thought of as a strip of vorticity, a swirl of water, right? And one of the things that's incredibly just interesting mathematically is that those strips of vorticity are generically not stable. They don't like being arranged like that. There's a real analogy with, the drip. Why do taps drip? Have you ever wondered why a tap drips? Right, so a stream of water breaks up into droplets because the interface is unstable. Another example of that is atmospheric pressure is 10 meters, is equivalent to 10 meters of water, something we all understand when we dive into water, right? You work out the hydrostatic pressure. But then stop and think about what the implications of that statement is. That means that in this classroom, in this room, which is sealed, we should be able to have a layer of water that covers you, right? Because atmospheric pressure would keep it up. So why does water fall out of a bucket? Why water falls out of a bucket is because the interface is unstable. There are arrangements of fluid that are unstable. It's called the Rayleigh-Taylor instability. It's why water falls out. This strip of vorticity is unstable and then forms into vortices, elliptical vortices called this Kelvin-Helmholtz billow is an example. And you see this, if you look up you regularly see this if you know what you're looking at, in the clouds. You can see these large swirls of arrays of swirls of vortices. But if you look at them, you don't see you see those swirls for a while and then they break down. They go unstable. And these extreme events, we believe, are a situation where the flow arranged it, so it wasn't turbulent, it got organized into this nice shear, and then formed these beautiful big vortices, and those big vortices then broke down. And so it is a rare event where you are well organized to get big vortices before you get little vortices. Most of the time you only have little vortices, but sometimes you can have big vortices before you have little vortices. Like this, that's exactly what you see here, right? You have had a big vortex and you got little vortices growing on it. It's this case we believe corresponds to that case. Because this will have high dissipation, but so will lots of little vortices. But you have to have had this big washing machine to start with to have a big overturning to mix. Because there's another example which is known to everybody. It's not exactly mixing because of course it's emulsion, right? How do you make a salad dressing, right? You put the oil and the vinegar in and you don't stir it sedately around. You turn it upside down, right? That process of having dense stuff over light stuff is the very, very efficient way to mix things. And so you have to get that organized, and the way you're going to get that organized is by one of these big Kelvin-Helmholtz billows. And that will happen rarely, because it's got to be quiet beforehand. You've got to have a lot of shear, a lot of kinetic energy, but you've got to not break it down before it can get big, right? So you have to have this flaring, this big washing machine. So that's our hypothesis of why it's happening, because that, from our numerical simulations, is consistent with what we observe, right? But the numerical simulations are very idealized, but that's classical physics, right? You do an idealized experiment and you say you now have explained the world.
Any other questions? If not, feel free to ask questions afterwards if you want to ask a bit more informally. But if there's no more questions, can we give a round of applause again?
Thank you.